Okay. Um, so today we're going to talk about mass balances. I'm going to business school in the fall, making a little bit of a pivot, but I don't really want to lose touch with, what I've learned about chemical engineering. So I'm going to start making some videos that are on chemical engineering topics. We've definitely talked about different bioprocessing things, and they incorporate topics from chemical engineering. But I figure I'll focus directly on just some chemical engineering related topics, starting with mass balances. This is kind of like the bread and butter of chemical engineering, I feel like. Um, yeah, so this video is just going to be an overview of some things on mass balances with simple example at the end, and then I'll do some other videos that are with maybe more involved mass balance problems. So, what is a mass balance? I like to think of it as an accounting of mass in a system, right? It's like just an accounting problem. Where did everything go? So up here I have a little diagram um, right here where we have MI, mass in, and MO, mass out. MI goes into this box and then out the other end. The box is our system here. This can be many things, some sort of unit operation. It could be a box. Um, and, we know that mass is conserved, right? So, like the mass going into the box should equal the mass out, right? For this example, we could consider that we have our MI here is sand. Like we have a pile of sand and we put it into a box and then we dump the box out. All the sand goes back on the floor or whatever, and that's our MO, our sand out. So what if your sand in, your mass in does not equal your mass out? Well, there's, a few things that could be going on. Um, you know, First, you could have a bad measurement. I don't know, maybe you're weighing the sand and maybe there's a user error with the scale, or um, there's an issue with the scale. It's yeah, broken, but in between, measurements. Who knows? But you have a bad measurement. That's one possibility. Um, there could be a leak. There could be a leak in the box or the system. So maybe there's a hole in the box, and then when you went to dump the sand back out onto your scale, some of it stayed on the floor. Um, so those are two possibilities. The sand could be consumed by some reaction. Maybe there's a chemical reaction that happens inside the box um, that consumes some sand and turns it into air. Who knows? And then there's also generation. Maybe there is, you put your sand in the box and all of a sudden you have more sand on the way out. There's a chemical reaction that produces more sand. So that's another possibility. These are the cases where your mass in does not equal your mass out. And one and two, these ones here, wrong measurements and leaks, those can certainly happen. But we will, generally assume that our measurements are accurate and there's no leaks. When you're doing stuff in the lab, uh, you know, these become more real, but when you're doing problems in your mass and energy balances class, unlikely that those are going to be happening. Um, so then our three and four, these happen if we have a reaction. If we have a reaction, it could be consuming a substance or creating a substance. So that's when three and four come into play. And those you will see in your mass and energy balances class. So here, we have um, this here is the general mass balance equation. We have your mass in minus your mass out plus your mass generated through a reaction minus your mass consumed through a reaction is equal to the mass accumulated in the system. This is your general mass balance equation. You're going to see things of this form a lot in chemical engineering. You're going to use this equation a lot. But in the problems that we'll solve, often there are often many simplifications. So the first one is steady state. Bear with me, I'm using a mouse here to write this. So it's written really poorly and slowly. So we have steady state, and in this situation, your accumulation term is equal to zero. So this term goes away. That term goes away. This one, that goes away. It's equal to zero. You're definitely going to see this a lot. Steady state. We prefer things to be in steady state. Things or times when you don't see the steady state assumption are when you have like batch processes that are like time dependent. Um, in those instances, right, where you're, accumulating things over time, or like you could envision like a batch reactor and you put in components A and B, and over time they turn into C. Your amount of C over time will increase, and A and B will decrease as they react. So, um, yeah. So steady state, your accumulation term is zero, goes away. And then next, we talked about what if the mass in doesn't equal the mass out for a certain species, right? We said that could happen for the four reasons above. Gonna scroll up to these. But in the equation, like I was saying before, we'll ignore one and two for all practical purposes here, but three and four, generation consumed, those have to do with reactions, and we definitely deal with reactions in chemical engineering. So um, if we have no reactions, no reaction, and steady state, we get our I guess so. Actually, let me go back. No reaction, your generation and your consume terms, these go away. Those completely go away. These ones gone, which is nice. So if you have steady state and no reaction, you get a very simple mass in is equal to mass out. Very simple equation. Mass in equals mass out. That's if there's no reactions. But we do have reactions, and things become a little different when we do have reactions. So I have this table here where we're asking, is it constant? It being, it is mass we're talking about. And if there's no reaction, if there's no reaction at all, like we have our sand that we're putting into the box and then dumping out, the total amount of sand will be constant. The total moles of sand will be constant. Molecular species maybe so I guess in the sand example, your molecular species is equal to your total mass. But let's say that we also have like Legos mixed in with the sand. Well, then the mass of the Legos will be constant, and the moles of Legos will be constant. The mass of sand will be constant, and the moles of sand will be constant. But then the total mass, so sand and Legos combined, and the moles, sand and Legos combined, those will also be constant. And then we have our atomic species. So I guess my sand example kind of falls apart here for like my chemistry knowledge. I don't know what sand is made up of. sue me. But we could maybe talk just about, I guess, water real quick. Let's say we have water. Um, your atomic species, now that's your hydrogen. You could do hydrogen balance, the amount of hydrogen that goes in, or oxygen, amount of oxygen that goes in and the amount of oxygen that comes out. And those will also be constant. Um, if you do have a reaction, things become a little different. So your total mass will remain the same. Your total moles, not necessarily. So just to illustrate that example, let's say you have component A plus component B turning into component C. So you have 1 mole of A, 1 mole of B. That's 2 total moles going in, and then 1 total mole coming out. So you can see that the total moles is not necessarily constant. Um, so then along that same uh, thought there, that's with that same example, the mass of molecular species and the moles of molecular species, so like your water molecules, those don't necessarily remain constant. Um, but your atomic species, these will remain constant. So that is a kind of, nice feature about like if you're doing a mass balance, you can stick with your atomic species because like your hydrogen atoms in will equal your hydrogen atoms. So that is kind of nice. Um, so then I guess the last couple things to touch on before we get into our quick example problem is like, the steps for solving. Steps for solving. Okay, so first things you'll do is you should always draw it out. Draw out the problem, draw the feed streams in, draw the feed streams out, write the information you know. Next, we will have, um, select your units. You might get some problems where some things are given to you in kilograms, others in grams, maybe some are in moles, some are, I don't know, just different units, hours, mass per hours, mass per minute. Standardize everything always helps. That's, it's a pretty minor thing, but it certainly helps. Select a basis. You're not always given a basis, meaning like, you could have something where it's like feed stream A goes in and 50% of it is converted into feed stream B. Well, to solve the problem, you might need to pick a mass rate in or amount of mass you're working with. Pick something easy, 10 kilograms per hour, it's something easy. So sometimes you'll have to do that. Other times it'll be given to you. And then the last thing that is important is um, stating your assumptions. Sometimes these problems get complex, and you will need to say that you're assuming things like maybe all of a certain reactant is consumed, or I don't know. They'll come up in some of the other problems we'll do later. And it's important to state those assumptions, like um, maybe that the temperature is room temperature if it's not specified, or that the density of something is equal to water, and so on. I'm struggling to think of some good assumptions to state right now, but they will definitely come up in our later videos. Um, and then there's some other stuff for solving too, like determining if the system is underdefined, overdefined, or so on. So, we'll talk about that, I guess, a little more later. I don't think I want to, yeah, I'm not going to talk about that right now. We'll just move into our example. But yeah, so like you can do things to figure out like if your system is overdetermined or underdetermined, meaning like is it solvable? Is there a unique solution or are there many solutions to the problem? And that's something that like for more complex problems, you should check. In my experience, my teachers never were so cruel as to like give me an exam and then not have the problem be solvable. But I don't know. Maybe my teachers were just always really nice. And then I guess the last thing I'll note is, and we won't really touch on that in this video either, but like there are nice, clean ways to set up like your systems of equations to solve these problems. Sometimes that helps. I never really did that too much. But like some people will set up like a nice table where they're like, this is the, here's what I know and don't know for my total mass balance. And here's what I know and don't know for this particular chemical species and this chemical species and so on. I never really like doing that too much, but I'll probably set up some of my um, later videos like that. So now let's just do a very simple um, practice problem. And I'm just going to copy and paste in the prompt I made. Okay, so here's our practice problem and put it up here. We have a cell slurry is fed to a continuous rotary vacuum filter at a rate of 100 kilograms per hour. The slurry is composed of 5% cells, 20% protein, which we're calling our product, um, and the remainder is water. All the cells are collected in the filter cake, and the protein recovery in the filtrate is 90%. The rate of filtrate collection is 90 kilograms per hour. And then we need to find the mass flow rate for the product or the protein. And that's in the filtrate. And then the water, the mass flow rate for the water in the filter cake. Um, yeah, so pretty simple problem here. A rotary vacuum filter, I mean, it's not necessary to know what that is for this problem, but from what I remember, is it's like this like spinning thing here, and then you like have your liquid go onto it and it turns, right? And then like all the liquid that you want to keep might like drain this way, and then like the cake, like in our case, the cells like builds up on it here, and then you have like this scraping thing that like will scrape it all off and it goes that way or something like that. Again, not necessary for this problem. Um, Yeah, I just modified a problem that I had um, seen a while ago for this. So anyway, so first things first, we'll draw our diagram. This box, this is our rotary vacuum filter. We have our inlet stream. We have our in one outlet stream. This is our filtrate. And then we have our filter cake. This is the filter cake. Okay. In our inlet stream, I'll just label this to slurry. This is our slurry. Okay. So now the other part of drawing this is we need to write everything out. So we have a total of 100 kilogram per hour here. The filtrate, we were told we have 90 kilogram per hour. We have 5% are of this inlet slurry are cells. So 5% of 100 is going to be 5. I'm not going to write the units again. I'm just going to write cells. But this is 5 kilograms per hour. Of this total, 5 of it are cells, kilograms of cells per hour. 20% is the protein. So 20% of 100, 20. I'm just going to call this pro, but remember those units are kilogram per hour. And the remainder is water. So that means 75 kilograms per hour is water over here. And then we were told that all the cells are collected in the filter cake. So if we have 5 cells, 5 kilograms per hour of cells in, over here, we're going to have 5 kilograms per hour of cells out. And then we were also told that the protein recovery in the filtrate is 90%. So that means that we are going to have, well, I guess I made this a little too easy, but 90% of 20 is 18. 18 cells. Okay. 18 kilograms per hour of cells leaving in the filtrate. So I guess we touched on this a little before, and I said I wasn't going to do it, but I'm going to write it out here. So like if you were doing your total mass balance, your total, you have your inlet stream and you have your filtrate stream. And then you also have your cake, your filter cake. You have that stream. So if you're doing your total mass balance, right? We have 100 in. We were told that there was 90 going out, kilograms per hour going out in the filtrate. So then your cake, initially this is just a question mark, right? But we have no reaction. So your in is equal to your out, right? Your in's equal to your out. And these two streams, those make up your out, your filtrate, right? Filtrate, and then your filter cake. Those are your out streams. In equals out. So the filtrate plus the cake, these need to equal your in stream. I'm going to get rid of all that actually. So this is obviously 10. And then we can do the same thing with all our species. So this is what I was talking about. People like write their mass balances out in these nice tables. In a simple problem like this, it's super easy to do. I don't like doing it when things get complex and my work is a mess. It's all over the place, but it works for me. So whatever works for you, do that. So for the cells, we know we had 5 kilograms per hour of cells coming in. We know none of it got converted to the filtrate. It was all collected in the cake. That came from the word or the problem statement. So that means we have 5 in the cake. For our protein, we had 20 kilograms per hour going in. The recovery in the filtrate was 90%. So that means there's 18 kilograms per hour in the filtrate. And then remember, I'm going to write this again. In equals out in this problem where it's steady state. There is no reaction going on. In equals out. So in the cake, we have 2 kilograms per hour. And then finally, we have our water where we had 75 kilograms per hour in. And okay, so now we get to, I guess, do a little bit of solving. So we have 90 kilograms per hour in our filtrate. and 18 kilograms per hour are of the cells. We were able to determine that from the tidbit about recovery that we got. So that means the remainder, 72 kilograms per hour, must be water so that we can get to 90 kilograms per hour total in this filtrate stream. And then that, going back to our N equals out, the filter cake must have 3 kilograms per hour of water leaving. So yeah, that concludes this video. A little sloppy, but you got to bear with me. I'm just kind of doing this for kicks and giggles here. I hope that you learned something about what mass balances are. This was a super simple example problem. I'll definitely do a couple that are more complicated. And I'll touch on, determining, if your system is like overdetermined, underdetermined, and what that means. Um, yeah, I hope you liked the video. I hope it helps a little bit. This will be the first of a few videos on mass balances, and I'll see you later.